All right, this is Miss Whitaker, and wanting to go over some notes that we went over in pre-AP class today on scale and scale factor. So I wanted to start with the first page that went over some of the vocabulary that we needed to know. And we'll just start up at the top here with scale drawing. A scale drawing is a two-dimensional drawing that accurately represents an object. So two-dimensionals, make sure you understand what that means. That's basically length times width. Length and width are the two dimensions we're talking about here. So it's basically flat on the paper is two-dimensional. So that's our drawing, scale drawing. Accurately means proportionally. So I want you to add these additional notes. Accurately means proportional. If it's to scale, if it's drawn to scale, it means they're proportional to the actual object. All right, next we're going to look at scale. Definition of scale is the ratio of the dimensions of a drawing and the actual object. So the ratio. What does that ratio make you think of? Probably a fraction, and that's good. So when you hear the word ratio, I want you to think of what a fraction would look like. And that fraction is going to be made up of the dimensions of the drawing and the actual object. And just to be a little bit more clear, we're going to say the drawing dimensions are going to be on the top, because it's going to look like a fraction, and then the actual object or the original object's dimensions are going to be on the bottom. So keep that in mind. Also, I want to make sure you understand that with scale, it can be in different units, and it actually usually is in different units. Now, it's kind of hard to say, but anyway, it can be in different units. It usually is in different units. Think of a map. When you see a map, you think of the little scale that's in the corner that says, oh, 1 inch represents 5 miles on the road. So you've got inches and miles. Those are in different units, and that would be your scale. Now, we're going to talk about scale factor in a minute, which has to be in the same unit, so I wanted to make sure we differentiated between those two things. Moving on to scale model, same thing as above. You're going to be proportionally representing an actual object, but this time it's going to be 3 dimensions. So instead of just length times width, it's going to be length, width, and height. So when you think of a scale model, you think of your model trains or your model planes or model cars. Those kinds of things are going to be 3-dimensional, so you can actually hold it. All right, reduction. Now we're going to be talking about how we have our actual object, and we're either going to make it smaller or we make it bigger, and that goes with these two words here, reduction and enlargement. Reduction is a decrease in the size of all the dimensions in the same proportions. That's very important to remember. And we're going to talk about scale factor here in a minute, and in a reduction, the scale factor is going to be less than 1. So say I'm wanting to do something, oh, I want to take a big poster and I want to put it on the paper here. So I'm going to think of, well, I'm going to be reducing that. My scale factor is going to be a fraction less than 1, because 1 is going to be the dimensions of my actual object. So if I want to make it smaller, then my scale factor is going to be a fraction less than 1. And on the flip side, enlargement is when I'm making something bigger, when I'm making an actual object and making it bigger. So my scale factor is going to be greater than 1 when it's an enlargement. All right, let's go over some of these examples here. Make sure you see that, as we mentioned up above, the scale is going to have the scale length dimensions on top and the actual object's length dimensions on the bottom. And they are setting up a proportion, which we've already studied, so you should know how to do that. So what we're told is that the length of an object on a scale drawing is 2 centimeters. So on the drawing itself is 2 centimeters, but the actual length of the object is 8 meters. Now we're told the scale is 1 centimeter to blank meters, and we're wanting to know what that meters, what the actual object's dimensions are according to 1 centimeter on the scale drawing. So we're going to set up our proportion, and you can do 2 centimeters represents 8 meters, and you can put that on the left. You could flip those if you wanted to. It's probably what I would do. If I know 2 centimeters represents 8 meters, then 1 centimeter represents blank meters. So then I would use my cross products and solve to find out how much 1 centimeter represents on the actual object. So it turns out to be 4 meters using my proportions to solve. So hopefully that's okay. That's clear. All right, take a look at on the back of those notes. We've got a microscope problem, which you may see occasionally, and you know that when you look under a microscope that the actual object appears much, much bigger. That's the whole purpose of the microscope. So your scale's dimensions are going to be much bigger than the actual object. Say in this case an amoeba. Amoeba is very small. We can't even see it with the naked eye, but with a microscope we can see it. So the appearance of the amoeba is going to be big in our scale's dimensions. So what we're told is that the microscope view is 1,000 to 1. And it says when we look in that microscope view, the amoeba appears to have a length of 8 millimeters, and they're wanting to know what's the actual length. So the appearance is 8 millimeters, so would that go on the top or the bottom? Well, if the top number is our scale, is what it appears to be, that 8 millimeters is going to go on top. So we put it in our proportion. We're going to put the scale on one side, so 1,000 to 1, and then we're going to put that 8 millimeters because that's what it appears to be. That's not the actual length of the amoeba, so that's what it appears to be, and we're looking for the actual length. So we set up our proportion, use cross products to solve, and what we find is that the amoeba is actually 0.008 millimeters, which makes more sense because we can't see that with the naked eye. So make sure you're really careful with these microscope problems that you're putting the scale, what appears in the microscope is your scale dimension, not the actual dimension. All right, let's look at the next example. A model of a 27-foot tall house was made using the scale 2 inches to 3 feet. So remember, this is our scale. What's the height of the model? Now in this case, we are going to find the scale factor. So over here, I want you to put that this is the scale's dimensions, again, over the original object's dimensions. And the key here is that must be same units. So looking at our example here, we've got this model of a 27-foot tall house. We're given the scale that 2 inches on the model represents 3 feet of the house. So what's the height of the model? Now what we needed to do is, since this is a scale factor, we're going to change these units to the same thing. So let's change our feet to inches. So 2 inches represents 3 feet. So changing 3 feet to inches, we find they have 36 inches. So now we have 2 inches to 36 inches. We reduce that 1 to 18. So here's our scale factor. And we can say that this model is 1/18 the size of the house. Now we knew we couldn't say it's 2/3 the size of the house. That would be a very big model. And because the units were different, that's okay for our scale, which is different. But when we're talking scale factor, that's going to be a ratio that must be in the same unit. So we had to convert before we came up with that ratio. All right, once we got our scale factor, we're going to use that as part of our proportion. If 1/18 goes on the left here, and we're looking for, where do we get the 324? Well, since we're talking about inches here, we had to change the 27 feet to 324 inches. So we set up our proportion and solve, and we found out that the height of the model is 18 inches for that 27-foot tall house. So it's very helpful using scale or scale factor to come up with actual objects, dimensions, or vice versa.